All right, so now we want to talk about using derivatives to find maximum and minimum values and to sketch our graphs. Okay, so we're going to start by talking about where a function is increasing or decreasing. Now, if we have a graph in front of us, it's easy enough to see as we move from left to right, just like when you read a book, we go from left to right. If it looks like the function is going up a hill, that's increasing. If it looks like it's going down a hill, that's decreasing. The algebraic way to look at that is as my x values get bigger, my y values get bigger. So if as my x values get bigger, my y values also get bigger, then the function is increasing. And you might want to substitute the words I used where I put those green lines. So if my x values are getting bigger and my y values are also getting bigger, the function is increasing. Function is decreasing if as my x values get bigger, my y values get smaller. Okay, so that's where a function would be decreasing. Okay, so let's look at the graph real quick. So let's say I have this graph. Oops. Okay, over here, if we drew in tangent lines, okay, we would say that the slope of that tangent line, it's pretty steep, but it's a positive number, whatever it is. We could say it's +4, I don't know. Okay, and here, it's not quite as steep, so maybe it's a +2. Okay, again, the positive being the important part. Over here, we're getting a little flatter, so maybe that's a +1. Okay, and up here, right, it's still positive. Maybe it's a 1/2, but again, it's still positive. On this side, where the section where we would say that this graph was decreasing, this side we would have said it was increasing, you'll notice that the slopes of the tangent line are negative. All of these tangent lines are going to have negative slopes. Okay, so in sections where it's increasing, you'll notice the slopes of the tangent line have positive slopes. In areas where the graph is decreasing, the slopes of the tangent line have negative values. Okay. So if we have a derivative and the value is greater than 0, the value is positive, then it is increasing in that interval. If you take the derivative and plug in an x value and you get a value less than 0, a negative number, then you're decreasing in that interval. So we're increasing if the slopes of our tangent lines are bigger than 0, or decreasing if the slopes of our tangent line are less than 0. Okay, positive numbers, negative numbers. What about when it is 0? And actually, let's go back and look at that. So right up here at the top, we have a horizontal tangent line. That is our turning point of our graph. It would also, in this case, be a maximum. It's the highest point we get to. So those are very important points that we want to graph because we need to know where our graph's going to turn. These are called critical values. Okay, and critical values happen when our derivative is equal to 0. So we take our derivative and we'd set it equal to 0 and solve, or where our derivative does not exist. Okay, this is how we're going to find maximum and minimum values. These critical points are going to give us our maximums and our minimums. Okay. Again, this looks like a lot of gobbledygook, so let's talk about this in English. In English, we are saying that you have a minimum value if that value is smaller than every other output. If the y value at the place you think is a minimum is smaller than any other output over that interval, then it's a minimum. And if it's bigger than any other output over that interval, it's a maximum, right? Minimum is the smallest value, maximum is the biggest value. Again, this is about our critical values. Okay, critical values are where our derivative equals 0 or does not exist. Okay, so the first derivative test for relative extrema. Okay, so, and this is easier to draw to show you this. So you're going to have a minimum if you are decreasing on the left and increasing on the right. That's what this says. We're decreasing on the left and we're increasing on the right. Okay, so this would give us a minimum. We're going to have a maximum if we're increasing on the left and decreasing on the right. And if we have the same sign on both sides, it's neither a max nor a min. And this is a real quick graph for you, same kind of thing that I just showed you. The slopes of our tangent lines are going to be negative on this side, positive on this side. That tells us we have a minimum. If we have positive slopes on this side, negative on this side, we have a maximum. And here's two examples of when we would have neither a min nor a max. So let's look at how this is going to work. We want to graph this function and find the relative extrema. Okay, so we could just try to plot some points, but we're going to use calculus to graph this. So the first thing we need to do is take a derivative. Okay, so let's take a derivative. F prime is going to be 6x squared minus 6x minus 12. All right, I want to move this to the next page so we can do some work here. So f prime of x was 6x squared minus 6x minus 12. Okay, this is a polynomial, so it exists everywhere, so we're not going to have a critical value from it not existing. So let's go ahead and set it equal to 0 and solve. So we're going to have 6x squared minus 6x minus 12 equals 0. Okay, we need to factor this. So everything is divisible by 6. So let's go ahead and divide through all the way through by 6. So divide by 6, divide by 6, divide by 6, divide by 6. So we get x squared minus x minus 2 equals 0. And I want to factor that, so I need two numbers. They multiply to be a negative 2. They add to be a negative 1. So I'm going to say negative 2 and positive 1. So I have x minus 2, x plus 1 equals 0. So x equals 2 and x equals negative 1. Those are the x values. Okay, to get the y values, I need to take these numbers and plug them into our original function. And our original function was 2x cubed minus 3x squared minus 12x plus 12, I believe. Let me check that. Yes, plus 12. Okay. So we want to plug back into that to see what these values are. So let's go ahead and check that in our calculators. We're going to have 2 times okay, so it looks like we have 2 comma negative 8 for the first one, and negative 1, let's see what that gives us. And it looks like 119. All right, and to see whether these are maxes or mins, this is what we would do. We would draw a number line. Okay, our original domain is negative infinity to positive infinity, and we would put these x values on the number line, -1 and 2, in the order that they would appear. Okay, and then I pick a number here. So, and we're going to plug this number into the derivative. So remember, our derivative was this, 6x squared minus 6x minus 12. Okay, so let's see, maybe -2 would work. Number in between would be 0, and a number bigger, maybe 3. All right, well, 0 is real easy. We know that the answer there is going to be -12. So in this section, we have negative tangent lines. Let's see what happens over here. We have positive, and when I plug a 3 in, I also get positive. So we have positive, negative, positive. Okay, that means it's going up on this side and then down on this side. So the point -119 is a max. We're going down here and then up on this side. So that's a min. So this point is a min. I like to draw the pictures in. You might not have liked that part, but that gives us a good visual that this is a max and this is a min. So when it's decreasing, I draw that downward slope. When it's increasing, draw the upward slope. And on the graph, we can see that that point was a maximum and this point was a minimum. All right. So some steps in order to to graph these. We want to first find the derivative. We want to find where our derivative does not exist or where it equals 0. Okay, and here is where you'll see this is the same thing we just did. Our critical values were -1 and 2. Again, on the number line, they're saying in this section here, they used -2. The sign of the derivative was positive. That means from negative infinity to -1, that whole section is increasing. Okay? From -1 to 2, that whole section where they've labeled it as B, we are decreasing. And then from 2 all the way to infinity, we're increasing again. All right, so let's try another one. So we have this function. So let's go ahead and get f prime. We need our derivative, which is going to be 3x squared minus 27. Let's set that equal to 0 because it exists everywhere, so we're not going to have a problem with that. Okay, again, this has a GCF, so we're going to divide a 3 out everywhere. So we get x squared minus 9 equals 0, which factors to x plus 3, x minus 3 equals 0. Okay, so we get that x equals -3 and x equals +3. Now we have to figure out which one is a max and which one is a min. So we draw our number line, -3, +3. Remember, these are going out to negative infinity and positive infinity. Test numbers. So we want to plug numbers into this function. Now, I would advise putting that into your y equals because you've got to test 3 different numbers here. So let's just, the numbers I'm writing in here are nothing magical. They're just numbers I'm randomly picking because they live in this interval. 0 happens to live here, and we'll pick 4, okay? These have nothing to do with my number line. These numbers across here, they're just numbers that I am picking as test points. So if I plug -4 in there, I get a positive number. If I plug 0 in, I get a negative number. And if I plug 4 in, I get a positive number. So this was going up and then down. So at -3, we have a maximum. So -3 comma something. We're going to have to go back and find that y value. And then we go down and up. So at 3, we have a minimum. Let's go back to our original function and find out what that max and min are. So we have -3 gives us 48. So that's our max. And +3 gives us -60. So that would be our min. All right, let's look at one more. Okay, so this time we want the relative extrema for this function. So the first thing we need to do is find the derivative. This is a chain rule. So we're going to have 2/3 x minus 2 to the -1/3 times 1. And then don't forget we have that +1 at the end, and the derivative of the +1 is 0. So we would have +0. All right, so let's simplify this. Now, because my brain does not think in negative exponents, I'm going to rewrite this in a form that our brains think a little better in. So that negative exponent means everything to that exponent goes down to the bottom. So we have 2/3 cube roots of x minus 2. Okay, so remember, there are 2 places where we're going to have critical values. One is when we set this equal to 0, and the other is where this does not exist. Now, this one has an x in the bottom of a fraction, so it not existing is a very real possibility. So let's do both of those. Okay, so if I set this equal to 0, so I have 2/3 cube roots of x minus 2. And equal to 0. Now, the only time a fraction will ever equal 0 is when its numerator, meaning top of the fraction, is 0. So we don't need the denominator for this. We're going to set 2 equal to 0. That is never going to happen. So we do not have any critical values from it equaling 0. We could still have critical values arising from the possibility that it does not exist. Now, when we're looking at the domain problems, we're only going to set the denominator equal to 0. Okay, so let's divide both sides by 3. So we have cube root of x minus 2 equals 0. Now we're going to cube both sides. So we get x minus 2 equals 0 cubed, which is still 0. and add 2 to both sides. So we get that x equals 2 is a critical value. We do have a critical value that came from where this does not exist. So we have one critical value. I want you to think about what you think this graph might look like. Okay, I want you to get a picture in your head of what you think this graph is going to look like. Let's go ahead. We had the critical value of 2. We can plug that back into the original because it wasn't a problem in the original. So 2 minus 2 is 0 plus 1. So 2, 1 is our max, min, something. Okay. And here they've tested 0 and 3 and found that we have a negative on this side and a positive on this side. So it's going down and then back up. So this is definitely a min. Okay, so we're decreasing from negative infinity to 2, and then from 2 this way we are increasing. All right, and let's see what that graph might look like. Now, I'm wondering if this matches the picture that you had in your head, or if the picture you had in your head might have looked a little more like this. Okay, the difference between these two is something we call concavity, and that is where we will pick up next time in 3.2.